Hi, y'all. How's everyone doing today? Today we're going to be talking about chapter 4, which is all about global climates and biomes. Okay, so a lot of the things that I'm going to talk with you about today really build on each other, so you have to try your best to pay attention, okay? I know that we've been going over a lot of these things in class with the station labs and stuff like that, so I'm hoping that you hearing this the third time, right, because you were supposed to read the short sections in your book, and then you were also supposed to do the station labs. This will kind of be that third time of hearing it, and it's really going to stick in your brain. Okay, so let's talk about the difference between weather and climate. That's the first thing, all right? You've all heard about both of these terms, but maybe you've always been a little confused about them, okay? Weather is what happens on time scales from seconds to days, all right? We live in Texas. You never know if it's going to be, once December rolls around, if it's going to be 80 degrees one day or 40 degrees the next, right? That's weather. Climate, on the other hand, is the average weather that occurs in a given region over a long period of time. Usually we're talking several decades, something like that, okay? It's not really possible for us to predict weather more than a few days or weeks into the future, but we can make general observations about global, regional, and even local climate, okay? For example, areas close to the North and South Poles are considerably colder than areas that are close to the equator, where they're a lot warmer, right? Areas at high elevations are colder than nearby sites at lower elevations, if you guys have ever experienced going up in the mountains. Areas near the equator typically receive tons of rain, whereas regions at latitudes around 30 degrees north or 30 degrees south receive very little rain, okay? So like we talked about, these regional differences in temperature and precipitation help determine which organisms can survive in each region. We talked about that a little bit when we did our chapter 3 stuff. In order to understand these differences, we have to look at the processes that affect how heat and precipitation is distributed across the globe. Okay, so we're going to talk about 5 different processes today. They're listed right here. Okay, so let's talk about the atmosphere. All right, in order to understand those 5 different processes, we first have to have a good understanding of the atmosphere. So some of the main things that you need to know about the atmosphere, or the layers of the atmosphere, is that they are more densely packed closer to the Earth and less densely packed as you get further away from the Earth. Okay, so they're more densely packed down here and less densely packed as you get further away. Okay, so the first layer, the one closest to the Earth, is called the troposphere, right? The troposphere is the most dense layer. It's closest to the Earth. This is where there's lots of circulation and mixing of liquids and gases, stuff like that. When we talk about weather, weather occurs in the troposphere, okay? The stratosphere is really important. This is a layer above the troposphere, okay? But it's important because this is where the ozone layer is. So you may have learned about or heard about the ozone layer before. If you look at the graph here, you can see that as you get higher up in the stratosphere, the temperature goes up, okay? So right here, you're at about negative 60 degrees Celsius, and this looks closer to 0 to 5 or something degrees Celsius, okay? This is because the UV rays reach the higher altitudes first and warm them as they get closer to the Earth. And when they do get closer to the Earth, they cool off a bit, all right? The ozone layer here absorbs most of the sun's ultraviolet B and ultraviolet C radiation. We're going to talk a lot about this year when we talk about air pollution and stuff like that. But UV radiation, and you guys have probably heard this before, can cause DNA damage, it can cause cancer, and all sorts of nasty stuff like that. So the stratospheric ozone layer is very important for us, okay? One of the other things that you guys have to know is that the mesosphere, the thermosphere, and the exosphere, they go in that order, right? So you've got troposphere, stratosphere, mesosphere, thermosphere, exosphere. So one of the things that I gave you here is this mnemonic. I can't get this thing to go away, but it's Thompson says, memorize this early. Get it? All right? Thompson, I use the Thompson instead of Thompson because thermosphere has the H and that's the this, so troposphere, I don't know, maybe you guys will remember it. Maybe you guys have heard of the northern lights. Here are some really pretty pictures here. You usually know them as aurora borealis, right? This is a phenomenon that happens in the thermosphere, okay? So the thermosphere has charged gas molecules, and when they get hit by solar energy, they begin to glow, and they look like this. It's super pretty. But it's the same way that a light bulb glows when electricity is applied to it, okay? I saw this the other day. I thought it was adorable. My son didn't want to be a tiger or a superhero. He wanted to be a traffic light. How cute, since Halloween's coming up, I guess. Okay, let's talk about this. The unequal heating of the earth, right? You have a lab in class that's talking about this. So as the sun's energy passes through the atmosphere and strikes land and water, it warms up the surface of the earth. You guys know that. But another thing that you also know is that this warming doesn't occur evenly on the planet in all places. Okay, so let's talk about the different reasons why this doesn't happen the same way in all these different places. So the first reason why that you guys need to know, and I have them listed here, is because of the angle at which the sun's rays strike the earth. Okay, so if you look at this diagram right here, the region nearest the equator, what we call the tropics, right? In that region, the sun strikes at a perpendicular or right angle, okay? And it's showing this over here as well. It's hitting at a right angle. In the mid-latitudes and polar regions, the sun's rays strike at a more oblique angle. So here you guys can see this oblique angle. As a result, the sun's rays travel a shorter distance through the atmosphere to reach the Earth's surface in the tropics right here. Okay, because solar energy is lost as it passes through the atmosphere, more solar energy reaches the equator than the mid-latitudes and polar regions. Okay, the second cause of this uneven warming of the Earth is variation in the amount of surface area over which the sun's rays are distributed. This perpendicular angle right here of the sun's rays in the tropics causes the solar energy to be distributed over smaller surface area. So you can see this circle right here, than at the higher latitudes, right? This is what it looks like at these higher latitudes, okay? There's more surface area, okay? So that given amount of solar energy is spread over a larger surface area than here at the equator. Because of this, you get more solar energy per square meter in the tropics than at mid-latitude and the polar regions. Okay. Third thing, all right, is called albedo, A-L-B-E-D-O. This is probably a new word to you, and we didn't really talk about this when you guys did your lab. So, some areas of the Earth reflect more solar energy than others. Okay, different types of surfaces, such as water, grass, forest, sea ice, cropland, etc., 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 reflect different amounts. Okay, so you need to know this vocab word. It's called albedo. It's listed right here, Earth's albedo. Okay, the percentage of incoming sunlight that's reflected from a surface is called its albedo. The higher the albedo of a surface means the more solar energy it reflects and the less it absorbs. Okay, a white surface has a higher albedo than a black surface, so it tends to stay cooler, right? That's why in the summer, you never go out and lay on the trampoline in your swimsuit because the trampoline is so hot, right? Or you don't ever want to wear all sorts of dark stuff out in the sun in the summer because it gets so hot. This is a perfect example of albedo, but we're just talking about the surface of the Earth and how much they reflect or absorb solar energy. Okay, so you guys need to be familiar with that. Okay, here we go. So now that you guys understand how the Earth is heated unevenly, right, we can now understand how uneven heating drives the circulation of air in the atmosphere. Okay, so a few weeks ago in class when we talked about plate tectonics, we talked about convection. Okay, that plays a huge part when we're talking about air. The density of air determines its movement. Just like we said in class the other day and like you saw in your lab, less dense air rises and denser air sinks. Okay, so the first property that really determines this movement is density. Okay, the second one that you guys need to be familiar with is water vapor capacity. Okay, so warm air has a higher capacity for water vapor than cold air. That's why in many parts of the world, including here in North America and especially in Houston, right, we usually associate our hot summer days with high humidity. Okay, the warm air contains a lot of water vapor. That's why you walk out and it's like you're literally drenched. The maximum amount of water vapor that can be in the air to a given temperature is called its saturation point. Okay, so basically, when the temperature of air falls, its saturation point decreases and water vapor condenses into liquid water. That's when precipitation occurs and when it rains. If it's hotter, the air can hold more water without it raining. That's why it seems so wet outside in Houston, because it's so hot that hot air can hold so much water vapor. Okay, as air rises higher in the atmosphere, the pressure on it decreases. Okay, the lower pressure allows the rising air to expand in volume, and this expansion lowers the temperature in the air. So this process, it's your third property right here, is called adiabatic cooling. Okay, oppositely, when air sinks towards the Earth's surface, the pressure on it increases. So the higher pressure forces the air to decrease in volume, and that decrease raises the temperature of the air. We call that process adiabatic heating. Okay, so these two things are happening over and over and over again, and I'll explain a little bit more about that in a second. The last really important property of air is a production of heat when water vapor condenses from a gas to a liquid. So like we talked about, the sun provides the energy necessary to evaporate water on Earth's surface and convert it into water vapor, which enters the atmosphere. Okay, in the reverse process, when water vapor in the atmosphere condenses into liquid water, energy is released. So we call this phenomenon, this last property here, latent heat release. All right, it's really important because it means that whenever water vapor in the atmosphere condenses, the air is going to become warmer and warm air will rise. Okay, here we go. So we've talked about the properties of air. Now we're moving on to talk about how these different properties play a role in atmospheric circulation. Okay, so let's pretend that we are in the tropics, we're near the equator. Atmospheric convection currents are global patterns of air movement that are initiated by the unequal heating of the Earth, which we just talked about. In the tropics, the warming of humid air on the Earth's surface decreases its density. So as a result, the air begins to rise. Okay, so when the air rises, it begins to experience lower atmospheric pressure and adiabatic cooling. Okay, the cooling causes the air to reach its saturation point. This leads to condensation, okay, which causes cloud formation, all right, and then eventually precipitation. It's going to rain, okay? Condensation also causes that latent heat release like we just talked about, which offsets some of the adiabatic cooling and becomes a strong driving force to make the air expand further and rise more rapidly through the troposphere. So altogether, these processes cause air to rise continuously from the Earth's surface near the equator, forming a river of air flowing upward into the troposphere, which you can see on the diagram that I'm going to show you here in a minute. So once it gets to the top of the troposphere, it's chilled by adiabatic cooling. Eventually, they're going to sink back to the Earth's surface at approximately 30 degrees north and 30 degrees south. Okay, I'll show you a diagram in a second. When the air sinks, it experiences higher atmospheric pressures, and its reduction in volume causes adiabatic heating. Okay, so by the time the air reaches the Earth's surface, it's really hot and it's really dry, right? So as a result, these regions at about 30 degrees north and 30 degrees south are typically really, really hot and really dry, okay? They're what we call deserts, and we'll talk about that when we get to our biomes. So a lot of this desert air then moves along Earth's surface towards the equator, and it replaces the air that's rising and completing the cycle. Okay? But these convection currents that cycle between the equator and then at 30 degrees north and 30 degrees south, okay, we call those Hadley cells. So you can see that right here. The area of the Earth that receives the most intense sunlight, okay, which is where the ascending branches of the two Hadley cells converge, right there on the equator, it's called the intertropical convergence zone. Okay, we also call this the ITCZ. Woo, that's a tough one. The ITCZ usually has lots of dense clouds and intense thunderstorms, okay? Because the latitude along which the ITCZ is located is not fixed. Over the course of the year, it moves north and south of the equator, following the path of the sun's most direct rays. So because the Earth's axis is tilted, right, at about 23.5 degrees, the area receiving the most intense sunlight is just between about 23.5 degrees north and 23.5 degrees south as the Earth orbits the sun. Okay, so as a result, that's why we get these tropics experiencing seasonal patterns of precipitation, lots and lots of rain. Okay, so there's another type of cells that are similar to these Hadley cells, but we call these polar cells. All right, these convection currents are formed by air that rises at 60 degrees north and 60 degrees south and sinks at the poles, okay, which are about 90 degrees north and 90 degrees south. At 60 degrees north and south, the rising air cools and the water vapor condenses into precipitation, okay? The air dries as it moves towards the poles, where it sinks back into the Earth's surface cells and the polar cells. So at Earth's surface, some of the warmer air from the Hadley cells moves towards the poles from 30 degrees north and south, and some of the cooler air from the polar cells moves towards the equator from 60 degrees north and 60 degrees south. This movement not only helps to move that warm air away from the tropics and the cold air away from the poles, but it also allows a wide range of warm and cold air currents to circulate between that 30 degrees and 60 degrees north or south. So all of these convection currents work together, okay? They're slowly moving the warm air from the tropics toward the mid-latitude and polar regions. This pattern of air circulation is responsible for the locations of our rainforests, our deserts, and grasslands and stuff like that. So when we talk about biomes, this is something that you should have fresh in your brain in order to help you understand why we have deserts and why we have rainforests and why we have these different types of biomes, okay? So this is a diagram of the formation of convection currents, and I basically just went through and explained this to you, sorry, but you've got your first step, right, at the ITCZ, that's right here. This red line right here represents where the sun would be hitting around the equator based on the tilt of the Earth on its axis, okay? So the ITCZ is where the sun is hitting, okay, right around. So once it gets up here and it becomes a dry, cold air, that's when step 4 comes into play. So you've got the warm rising air displacing the cooler air, and it's moving it from the north down to the south. You can see how it's going here in this little circle. It's not really circle, but cycle, whatever you want to call it. Then you get to step 5, right? So the cool, dry air sinks and experiences adiabatic heating, right? So it reaches the Earth's surface down here as warm, dry air, and then it's going to flow back here into or towards the equator, okay? And then the process just keeps going, boom, 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 boom. So you got your adiabatic cooling, adiabatic heating, cycle, 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 cycle. Done. All right, let's go. Oh, here, I got a joke for you. I love the way the Earth rotates. It really makes my day. Okay, let's talk about this. All right, so let's talk about the rotation of the Earth on its axis, all right? Woo! Let me move this over here. All right, so Earth's rotation has an important influence on climate, and you guys had a lab about this in your stations lab, particularly in the directions of the prevailing winds, okay? So as the Earth rotates, its surface moves much faster at the equator than at mid-latitude or polar regions, okay? This is happening because the planet's circumference, right here in the middle, right, is about 25,000 miles at the equator. Okay, but it decreases to 0 when you get to the North Pole or when you get to the South Pole. So imagine traveling around the Earth at the equator versus at the poles, right? Basically, at the equator, you have to travel much farther to go all the way. Basically, at the equator, you have to travel much farther to go all the way. Oh my God, I can't talk. Basically, I'm gonna put my foot up. Basically, at the equator, you have to travel much farther to go all the way around the Earth than you would if you were to be standing at one of the poles in the North or the South Pole. I said that. So if you're standing here at the equator, you're going to be moving at about 1,038 miles per hour. All right. If you're at about 30 degrees north or south, you're moving at about 898 miles per hour. And then if you're up here at around 80 degrees, you're moving at like 181 miles per hour. And obviously, if you're standing directly at the North or South Pole, you're just rotating. You're not really moving. But anyway, so the fastest rotation speeds closer to the equator cause deflection of objects that are moving directly north or directly south. Okay, so basically, if you're standing at the North Pole and you tried to throw a ball directly south all the way down to the equator, if the Earth did not rotate, the ball would travel south of the equator in a straight line. Boom. Okay? Makes sense. But because the Earth is rotating constantly, right? It's rotating to the east. While that ball is traveling, the ball will land in a location that's west of its intended target. In other words, the path of the ball is deflected with respect to a given location on the globe because the Earth is rotating. The deflection of an object's path due to the Earth's rotation is what we call the Coriolis effect, this weird word right here. All the different wind systems that we have on this planet are produced by a combination of atmospheric convection currents and this thing called the Coriolis effect. Okay, if the Earth didn't rotate, basically the air within each convection cell would simply move directly north or south and cycle back again. So consider the thing we were talking about earlier, right? A Hadley cell. So where the air sinks at the Earth's surface around 30 degrees latitude, Earth is rotating at about 898 miles per hour, right? But as the air travels along Earth's surface towards the equator, the Earth's speed of rotation increases, right? It's going up to about 1,038 miles per hour. So as a result, what happens is we have air movement toward the equator being deflected to the west. Okay, so that's why you can see these little red arrows here. So because of this deflection, the Hadley cell north of the equator produces prevailing winds along Earth's surface that come from the northeast, called the northeast trade winds. All these little guys right here. Okay, whereas the cell south of the equator produces prevailing winds that come from the southeast, and we call these the southeast trade winds, which are all these little arrows right here. Okay, so the Coriolis effect can also explain the prevailing wind direction in the mid-latitudes between 30 degrees and 60 degrees. Oops, up here. So these winds can be quite different as a result of the mixing air currents from these Hadley cells, which happen here, and the polar cells that happen up here. Okay, Hadley cells, polar cells. Closer to 30 degrees, right here, air tends to move along Earth's surface away from the equator. So basically, if the Earth wasn't rotating, this air would move straight north into the northern hemisphere and straight south into the southern hemisphere. But because the Earth is rotating faster at 30 degrees and 60 degrees, this air movement is simply just deflected to the east. Okay, so the combined effect of the air currents and the Coriolis effect causes the regions north of 30 degrees to experience prevailing winds from the southwest. In the southern hemisphere, the prevailing winds are from the northwest. Okay, so in both of these cases, we call these different winds westerlies. We've got the westerlies down here in the south and the westerlies up here in the north. Okay, so one other thing that the Coriolis effect is good for is that it helps us to understand these prevailing wind directions at the polar regions. So at Earth's surface, the polar cells are moving away from the poles towards 60 degrees latitude. Okay, given that the Earth is rotating faster at 60 degrees than at 90 degrees, their moving is deflected to the west. So because of this, the polar winds that come out of the northeast in the northern hemisphere and out of the southeast in the southern hemisphere are called easterlies. All right, so all of these different things combined right here, this picture does a pretty good job of explaining it, causes these prevailing wind patterns that occur all over the world. All right? Okay, so let's talk about this a little bit. You guys probably learned about this years ago, but you might not remember. So we were talking about the ITCZ, right? That's the latitude that receives the most direct sunlight on this planet. It's close to the equator, okay? But it shifts over the course of the year. So because the Earth's axis is tilted, it's at 23.5 degrees. Earth's orbit around the sun causes most regions all over the planet to experience all these different seasonal changes in temperature and precipitation. So specifically, when the northern hemisphere is tilted towards the sun, the southern hemisphere is tilted away from the sun and vice versa, okay? All right, so here's a little diagram here showing how this impacts things, okay? The sun's rays strike the equator directly twice a year during the March equinox, which is on March 20th or 21st, and again during the September equinox, which is on September 22nd or 23rd. We just had this a couple weeks ago, right? On these days, virtually all regions of the Earth are receiving 12 hours of daylight and 12 hours of darkness. So for the 6 months in between the March and September equinoxes, the northern hemisphere tilts towards the sun, experiencing more hours of daylight than darkness, and the opposite is true in the southern hemisphere. On June 20th or 21st, the sun is directly above the Tropic of Cancer at 23.5 degrees north latitude. All right, so that is the day that we call the June solstice in the northern hemisphere. And in the northern hemisphere, it experiences more daylight hours than any other day of the year. All right, so for those other 6 months between the September and March equinoxes, the northern hemisphere tilts away from the sun, okay, experiencing fewer hours of daylight than darkness. On December 21st and 22nd, we have the December solstice, right? And That's when the sun is directly over the Tropic of Capricorn at 23.5 degrees south latitude. But on that day, that's when the northern hemisphere experiences the shortest amount of daylight, and the southern hemisphere experiences the longest amount of daylight. So, giggity, giggity, goo. Okay, so let's talk about ocean currents real quick. Ocean currents are driven by a combination of temperature, gravity, prevailing winds, the Coriolis effect, and the location of continents. Okay, so like we already talked about, the tropics receive the most direct sunlight throughout the year. And as a result, tropical waters are generally warm, right? So like warm air, warm water expands and rises. This process raises the tropical water surface about 3 inches higher in elevation than mid-latitude waters. Okay, and this seems a little crazy, right? Because it's only a 3-inch difference. But even though that 3 inches seems trivial, it doesn't seem like a lot, the slight slope is sufficient enough for the force of gravity to make the water flow away from the equator. So even though it's just 3 inches above it, it's enough to make it flow. Okay, so let's talk about that a little bit. All right, so here's a beautiful map about ocean currents, oceanic circulation patterns, right? Global prevailing wind patterns play a major role in determining the direction in which ocean surface water moves away from the equator. In the northern hemisphere, for example, the trade winds near the equator push water from the northeast to the southwest, and the Coriolis effect deflects this so that the water is actually moving from east to west. Okay. Similarly, when winds at northern and mid-latitude regions push water from the southwest to the northeast, the Coriolis effect deflects this current so that water actually moves from west to east. Okay, so if you look at the diagram here, it's showing this overall effect, which is ocean surface currents rotating in a clockwise direction in the northern hemisphere. So you can see these are rotating here. You got the clockwise direction. And in the southern hemisphere, it basically puts them in a counterclockwise direction. Okay, southern hemisphere right here. We call these patterns here that are rotating, clockwise, counterclockwise, we call these gyres, Gyres. We're going to talk about gyres a lot throughout the whole entire year, but mostly we'll be talking about these when we get to our plastics unit, okay? Because you can imagine what might happen here in these gyres. Essentially, it's like a really slow flushing toilet. Okay, so anything that gets into these circular ocean currents is eventually going to end up in the middle, and there's not really any way for it to get out. Okay, so we'll talk about it more. It's really fascinating. But anyway, these gyres, they redistribute heat in the ocean, just like the atmospheric convection currents redistribute heat in the atmosphere. Okay, so cold water from these polar regions here, moves along the west coast of the continents, and the transport of that cool air from immediately above these waters causes these cooler temperatures on the land. So one really good example of this here would be the coast of California, right? So if any of you have traveled to California in the summer, you might be thinking, oh, it's going to be really hot on the beaches. But actually it's not, because it's bringing this cold air down from further north, okay? It's pretty cool. So there's a similar thing happening here as well, right? Water from the tropics, think about like the Caribbean and whatnot, that's moving along the east coast of the United States, and it's taking that warm air and that warm water there. So the entire east coast of the United States is actually going to end up being a lot warmer in the summer. All right, and we'll talk all about this too, because that Gulf Stream here is taking that warm water all across the Atlantic Ocean over to Europe. Okay, and that's why a lot of these countries over here, like Spain and France and stuff like that, they're warmer in the summer, even though they're so close to Greenland and Iceland and stuff like that. You would think they might be cold, but this warm air that's transported and the warm water that's transported by the Gulf Stream makes it a lot warmer. Okay, guys, so this is a vocab word that you guys need to know. It's upwelling. All right, so some regions of the ocean can support really highly productive ecosystems. All right, our ocean currents can help us explain why they can produce these ecosystems, right? So along the west coast of most continents, the surface currents diverge, okay, which means they separate from one another, all right, which causes deeper waters to rise and replace the water that has moved away. It's kind of like the Hadley cells with the air. Okay, so this upward movement of water towards the surface is called upwelling. Okay, this bringing up of all this stuff. So what happens when this water moves up, when it undergoes upwelling, it brings all sorts of nutrients from the ocean bottom, and it can support a large population of producers. Okay, so those nutrients are coming from the bottom of the ocean up to the top. All right, so the producers grow and they thrive, right? And when we have a lot more producers, we have a lot higher population of primary consumers and secondary consumers, and so on and so forth. So these are really, really important to commercial fisheries and stuff like that. Okay, so that's upwelling. You guys need to be familiar with that. Another oceanic circulation pattern that you guys should be familiar with is the thermohaline circulation. All right, this was a lab you did that was up at my desk. Okay, so this is driving the mixing of surface water with deep water in the ocean. All right, scientists know that this process is critical for moving heat and nutrients around the globe. If we did not have this thermohaline circulation, we wouldn't be able to do that. Okay, so this process appears to be driven by the surface waters that contain an unusually large amount of salt. On the next slide here, I'm going to show you a diagram, but it shows that the warm currents flow from the Gulf of Mexico. They go up to the very cold part of the North Atlantic. Okay, so some of the water freezes or evaporates, and the salt that remains behind increases the salt concentration or salinity, right, of the water. All right, so you end up with this cold, salty water, and it's relatively dense. All right, so what happens is it sinks down to the bottom of the ocean. And what you saw in your lab that you did in class is that exactly. So obviously the water that had the salt in it sunk down to the bottom, and that water that had salt was more dense than the cold water. So water that's cold and salty has high salinity is definitely the most dense type of water. Okay, so what happens in the ocean is you get this cold, salty water sink to the bottom of the ocean, and it mixes with the deeper ocean waters. There's two different processes that kind of come into play here. Okay, one, you've got the cold, salty water at the high latitudes, and the second thing is the rising of the warm water near the equator. Those two things create the movement necessary to drive a deep cold current that slowly moves past Antarctica and northward into the Pacific, or the northern Pacific Ocean, I guess I should say, where it returns to the surface to mix, and then it makes its way back to the Gulf of Mexico. So if you guys look at the diagram here in a second, you can see this whole entire round trip. All right, this round trip can take hundreds and hundreds of years to complete. It's not a fast thing, but that's what thermohaline circulation is. It helps to mix the water all over the oceans. Okay, so here you go. Here's some more information about that. I forgot I had it here on 2 slides. Oops. Okay, but here's the diagram. All right, so you can see there are steps here. Go ahead and take a look at this because this will really help you. But it's showing, warm water flowing from the Gulf to the North Atlantic. Okay, so you've got the Gulf to the North Atlantic here, where some of it freezes and evaporates because it's getting up to this cold part. But once it gets here, the water is a lot more saltier and it's dense, so it sinks down, down, down. It's cold and it's dense, so it's turning blue. And then this goes all the way over here. Some of it goes up here to the Indian Ocean. Some of it here goes along Antarctica, right? The cold water travels along the ocean floor, connecting the world's oceans. And it's going all the way to 4, where the cold, deep water eventually rises to the surface and circulates back to the North Atlantic. Okay, so it's this ongoing cycle. Pretty cool. All right, let's talk about heat transport. I'm just eating some gummy bears here. I don't think these are vegan. I don't know. I'll figure that out later. Am I talking a lot? I feel like I'm really talking a lot. And I'm really tired. But it's okay, because I'm making this video for you. By the way, I'm sorry that I didn't get this out right after school. I've just been trying so hard, and it takes so long to do these. But it's okay. Okay, let's talk about heat transport, right? Ocean currents affect the temperature of nearby land masses. Okay, so for example, the ocean current known as the Gulf Stream originates in the tropics near the Gulf of Mexico, and it flows northeast across the Atlantic towards Western Europe. I was kind of just talking about that. So what happens is it transports that warm water from the tropics all the way across the North Atlantic, and it takes it to these latitudes that will usually be much colder, but it helps to moderate the temperatures there. Okay, so for example, England, their average winter temperatures are about 36 degrees Fahrenheit warmer than that of Newfoundland, Canada, which is located at a similar latitude, but it receives the cold currents coming down from the North Atlantic, while England is receiving the warm currents coming across from the Gulf of Mexico. So we'll talk more about this when we get to our climate change stuff, but one of the really big concerns involved in global warming is that these increased air temperatures could accelerate the melting of glaciers in the northern hemisphere, right? All of Greenland and stuff like that. And they could make the waters of the North Atlantic less salty if we have all that fresh water moving into the salt water. And you guys know what happens, right? When it's less salty, it's less likely to sink. Sorry. So you're not going to get that dense water sinking down. You're going to have less dense water floating around the surface. Okay, but what could happen here is that chain could potentially shut down the thermohaline circulation, and it could stop this transport of warm water over to Western Europe. So again, let me go back to this thing for you guys right here. If this happens, this would no longer be carried across here, and there goes Spain and France and England, all of the UK, all of these places being warmer in the summer and stuff like that. There goes all your grapes to grow wine, and France, no more wine. Lots of problems surround this, okay? So we'll talk a lot more about that when we talk about climate change. Okay? Jokes. Okay, I kind of made this one up, but it says, a panda bear walks into a boba shop. She says, I'll take an almond milk tea extra sweet with boba, which is my fave. All right, the cashier says, why the big paws? The panda replies, I'm not sure. I was born with them. It's pretty good. Okay, let's keep going. You guys, we're almost done. Just bear with me here. Where should I put my face? Is this good? Okay, there. And then I'll look over here. There. Okay, let's talk about El Nino, the boy. El Nino Southern Oscillation. Okay, so Earth's atmosphere and the ocean interact in a lot of different complex ways. Okay, so periodically, approximately every 3 to 7 years or so, all of these different interactions cause surface currents in the Pacific to reverse direction, which is kind of crazy to think about. But if you look at this diagram here, you can see this process. And first, the trade winds near South America weaken. Okay, so this weakening allows the warm equatorial water from the Western Pacific, okay, which would be right here, to move eastward towards the coast of South America. All right, that movement of water and air towards South America suppresses upwelling off the coast of Peru and decreases the productivity there, reducing the fish populations that live near the coast of Peru. Okay, so we call this phenomenon El Nino, all right, because it begins around December 25th, which is Christmas, right? Literally, the boy, El Nino, Christmas, haha. I guess it's not funny, but whatever. Anyway, so this whole phenomenon right here, El Nino, it can last a few weeks, it can be a few years. But when we have these periodic changes in the winds and ocean currents, we call them collectively the El Nino Southern Oscillation, or we call it ENSO, E-N-S-O. Okay, so that's a term that you guys should be familiar with. But basically, if we're talking about this on a global scale, the impact of ENSO includes cooler and wetter conditions in the southeastern United States. Okay, so that's when we get a lot of rain and unusually dry weather in southern Africa and Southeast Asia. So if we're ever having a year that has super crazy weather, it's probably an El Nino year. That's kind of a vague statement to make, but I'm sure you've heard your parents talk about it like El Nino, it's El Nino or something like that. So we'll talk more about this, especially when we get to climate change, because basically everything's just kind of backwards and strange. So anywho. Okay, so these are just the steps there, which are essentially listed here too. So make sure you guys are familiar with these steps and what ENSO is. And then we got one more concept we're going to talk about, and these are rain shadows. I'm sure you've learned about these when you were younger. Okay. But so now you know that we have all sorts of processes that affect the weather and climate, and that they operate on a global scale. Okay, I'm moving my face. But there are a lot of different local features as well that can do this, like mountain ranges. Mountain ranges play a huge role in how weather and climate, affect an area. So air moving inland from the ocean often has a lot of water vapor. Okay, so in a second, I'm going to show you this diagram. But when this air meets the windward side of a mountain range, which is the side facing the wind, okay, you guys should know the difference between windward and leeward. so the side facing the wind, it rises and it begins to experience adiabatic cooling, just like in those Hadley cells. Okay, so because this water vapor condenses as the air cools, clouds form and precipitation falls. Okay, just like in the Hadley cells, the condensation causes latent heat release, which helps to accelerate the upward movement of the air. So the presence of the mountain range causes a large amount of precipitation to fall on its windward side. So then you have this cold, dry air that travels to the other side of the mountain, which is called the leeward side, and that cold, dry air descends, okay, because it's more dense, right? But when it gets down there, it descends, it experiences these higher pressures, which causes adiabatic heating. So again, you have this cycle. It's happening again and again and again, right? It becomes warm and dry, and then it produces these conditions on the leeward side of the range, forming this region that we call a rain shadow. That's what the diagram will show you here in a second. But it's really common to see really lush vegetation on the windward side of a mountain range, and then really, really dry conditions on the other side of the mountain range, on the leeward side. So usually in tropical areas, the rain shadows tend to be on the western sides of the mountain ranges because of the prevailing trade winds. They're moving from east to west. Okay, in mid-latitude zones, like in North America, the rain shadows are commonly on the eastern sides of the mountain ranges because the prevailing westerlies move from west to east. So here's your diagram here, and you can see, so pretend this is Washington, okay? This is the windward side of the mountain. You have all this air that's full of water vapor. Okay, so you get a lot of rain here on the windward side, but the cold, dry air keeps continuing over. It gets to the other side, it starts to sink because it's cold and it's dry, but then you have adiabatic heating, and yeah, the cycle keeps repeating itself. So this is something you guys should be familiar with. It's a fairly simple concept if you understand the Hadley cells and stuff like that. Okay, so I think we're good with that. That's all the stuff from chapter 4 in regards to weather and climate. Now, in class, we're going to talk about biomes, all right? And when we talk about biomes, basically your reading guide and the project that y'all do will be sufficient as far as notes go. So I'm not going to make another video and have you watch an Edpuzzle on the rest of chapter 4, but you need to be familiar with the different biomes and understand the climatograms, which are graphs we'll talk about, based on the temperature and precipitation, because those are the two things that really make biomes distinct from each other. Okay, so here's today's riddle, right? Who makes it has no need of it. Who buys it has no use for it. Who uses it can neither see nor feel it. What is it? Okay, so we'll see if you guys can get that. I will tell you in class, and I hope you all have an amazing day. I will see you when I see you, hopefully tomorrow, and we'll talk to you later. Bye.